Good afternoon, everyone. My name is Lucian Pullen, and I will be your tutor for today. Today, we'll be doing or reviewing the law of universal gravitation and my colleagues, the law of universal gravitation and some fluid mechanics. So, we'll be doing some gravitation and some fluid mechanics. Gravitation and some fluid mechanics. Now, what do you need to know about gravity, first of all? When we get to a fluid mechanics section, I will review some things that you need to know regarding fluid mechanics. Okay, so starting off, I just want to check everything is still fine. I'm just checking if I'm actually producing sound for you guys. Yes, the mic is picking up my voice. So, the law of universal gravitation. Okay, now you have done some of these problems or similar type problems in high school. So I know that you know gravity, how it works, the gravitational constant, and all of that. In this case, we don't go into, you only go into Kepler's law in second year physics, okay? So Newton's law of universal gravitation, this is Newton's law of universal gravitation. So the law of universal gravitation, the law of universal gravitation. Forgive my handwriting. Okay, so the law of universal gravitation, it says that the force between two bodies, the gravitational force between two bodies is equal to the product of G, which is the gravitational constant, multiplied by the product of the masses, the two masses of the bodies, mass 1 times mass 2. You've all seen this formula, or at least most of you, divided by the distance between their centers squared. Okay, so that is the universal law of gravitation, where G is equal to 6,67, 4 times 10. This is according to Survey. We use Survey's value or constant, and that is Newton meter squared per kilogram squared. Okay, so there we have the universal gravitational constant and the law of universal gravitation. Okay, how do you calculate the free fall acceleration? Okay, the free fall acceleration of a body. So this is free fall acceleration. Free fall acceleration. Is it one word? Maybe I just want to make sure it's one word. Yet hyphenated. Free fall acceleration. So free fall acceleration is equal to G. That's the free fall acceleration. So it's G, the gravitational constant, multiplied by the mass of the Earth, me, over the radius squared. Now you can rewrite this formula as G times the mass of the Earth divided by the radius of the Earth plus the height that this thing is, this particle is above the surface of the Earth, and squared. This is basically R2, it's just split up. And this is how you get your free fall acceleration. Now, in order to do this, you need to know the constants of G, which you already know. The mass of the Earth, if you ever get such a question, you can just, if it's in a tutorial or something, you can look it up. and the radius of the Earth, similar thing. But if it's in an exam or test, they should give you those constants. We do not expect you to know them off by heart, but do confirm with your lecturer, please. Okay, so those are the main things we need to know about gravitation. We do not go into Kepler's law of planetary motion at this stage. And of course, the oldie but the goodie, you know that uh, the force due to gravity is just called the body's weight. Okay, so let's go to problem number one. Okay, three uniform spheres. Okay, and I will show you the image now. We have three uniform spheres of mass m1, which is 2 kilograms, m2, which is 4 kilograms, and m3, which is 6 kilograms. They are placed at the corners of a right angle triangle. But before, as shown in that figure, I will show you the figure now. Calculate the resultant gravitational force on the object of mass m2, assuming the spheres are isolated from the rest of the universe, meaning there are no other masses in their vicinity to have an effect on them. Now, in the real world, that is not the case because there's always other masses that will have an effect. Okay, so but before we do that, I just want to do this problem, and then we go to that problem because this one chronologically in your textbook is first, and I've highlighted it now. Control, I just enlarged it, and then we will do the problem that we just showed. Okay, so just want to bring that up, that problem. Okay, there it is. A 2 kilogram object and a 5 kilogram object are separated by 4 meters. Okay, so we have a 2 kilogram object. This is problem number one for us today. We have a 2 kilogram object. Let's make it a circle. It's 2 kilograms. And we have a 5 kilogram. So let's try to draw it to scale. It looks roughly about double that size. So 5 kilogram. So we have these two objects. They are separated by 4 meters. Okay. So the distance between them, 4 meters. First question. Find the net gravitational force exerted by these objects on a 50 kilogram object placed midway between them. Okay, so let me remove, they are separated by 4 meters. So the distance from their centers is 4 meters. And then we place, I'm not going to be able to draw this one to scale. By the way, it's not 2 kilograms or 5 kilograms, 2 kilograms, 500 kilograms, 200 and 500. So it's 200 and 500 kilograms. Okay. And then do we have a 50 kilogram object between them? That makes 50 kilograms object, a 50 kilogram object between them. And the distance between those two are exactly 4 meters. Okay, and the problem is find the net gravitational force exerted by these objects on a 50 kilogram object placed midway between them. So the distance between this one and that one is 2 meters. And between that one and that one is 2 meters. In these cases, we consider the mass a point mass. Okay, it doesn't have dimensions. Or the distance is just that the center of the 50 kilogram is exactly, the 50 kilogram ball center is exactly at 2 meters between them. Okay, that is how we can theorize it. Okay, so let's go. So first we need to find the force between the 200 kilogram and the 50 kilograms, and then the 500 kilogram and the 50 kilogram. And remember, gravity is attractive. So this one will be pulling the 50 kilograms towards the left, and this one will be pulling it towards the right. Okay. So Let's calculate. So force 1, the force between the 200 kilogram and the 50 kilogram, let's call it force 1, is going to be equal to G, the universal gravitational constant, multiplied by M. It's F1 equal to G by M1 times M2 R squared between them. So that's F1, the force between the 200 kilogram and the 50 kilogram. The distance between them is 2 meters. If we plug everything in, G is equal to 6,67 times 10 to the negative 11. Now, like I usually say, I usually don't add in the units during the calculations because they become, I run out of space. So it's a 200 of the first mass multiplied by the 200 of the second mass, and then the distance between them is just 2 meters. And we square that. Don't never forget to square. So the force between the 200 kilogram mass and the 50 kilogram mass, the force is equal to 1,67 1,67 times 10 to the negative 7 newtons. Okay, 10 to the negative 7 newtons. So here you have 10,000, that's 4, that's negative 11 plus 4, and then divided by 4. Okay, so that's what we have. The first answer, the force between those two, F1, and it is attractive. This one is to the left, to the left. Okay, so we have a 1,67 times 10 to the negative 7 force to the left. And then for the second one, force 2 between the 50 kilogram weight and the 500 kilogram weight, mass, sorry. So it's 6,67 times 10 to the negative 11. Multiply that by 500 and that by 50. Divided by the distance between them is also 2, and don't forget to square. You get an answer of 4,17 times 10 to the negative 7 newtons. See that these forces are on the same magnitude, order of magnitude. And this one is towards the right. So we have a force towards the right and we have a force towards the left. Okay, so if we were to add them, if we want to find F net, the net force on that 50 kilogram weight, the net force will be F1. It will be, in this case, I'm going to choose the right dispositor, so it's going to be negative F1 plus F2. Okay? Negative because I'm choosing a right dispositive. Okay, so it's, remember what was the force of F1? 1,67 times 10 to the negative 7 newtons plus you have F2, which is 4,17 times 10 to the negative 7 newtons. So the net force is, then you subtract 1,6, that is almost 2, so around 2, something, 2.5 approximately, times 10 to the negative 7 newtons. And the answer is positive, so it's towards the right. And you would have seen that from your answers, because this one towards the right is much bigger than the one towards the left. Now, so part B of this question. At what position should you place, other than infinitely remote, can we place that 50 kilogram between them so that the net force is zero? Okay, so F net must be zero. What distance between them where F net should be zero? Okay, so you just need to adjust the distance as you go along in order to get F net to be zero. Okay, F net must be zero. So let's check. Okay, in order for F net to be zero, the following must happen. If F net is zero, it means that this force F1 should be equal to F2, but they will be in opposite directions as previously determined in order for them to cancel out. So that means that the G M1 M2 over R squared should be equal to, let's call the 50 kilogram weight M3. Let's call it M3. So M1 and M3, and then G multiplied by M1, M2 in this case, which is the 500 kilogram weight, and M3, which is the 50 kilogram weight, and the distance between them. Now, this is the situation. We want to know where should we place the 50 kilogram ball between these two. Okay, so the distance between this one, remember the total distance is 4. The total distance is 4 meters. Okay, the distance here, we want to know this distance that we should place it. So let's call it x. So if this distance is x, then this distance must be 4 minus x. Okay, I hope you understand that. If the distance between these two balls is x and the total distance is 4, then the distance left over must be 4 minus x. So let's insert it like that. So we have G M1 M3 over x is the distance here squared, and then G M1 M2 rather M3 over 4 minus x squared. That's the type of problems that usually trip up, especially this x and 4 minus x convention. So here we can cancel M3, comes in both. Can cancel G, comes in both. So what we're left with is M over x squared, M1 over x squared, and M2, which is a 500 kilogram, over 4 minus x squared. From that, you see you are going to be left with a solving of x. Okay, so let's just simplify this even a bit further. It is going to be m1, which is the 200 kilogram, over just x squared, and this one is the m2, and it is going to be 16 minus 8x, if I'm not mistaken, plus x squared. So if you solve for it, minus x, so both of them are. And then you cross multiply, of course. You put in the weight, this is 500 kilos. This one is 300, or rather 200 kilos. X squared 16 minus 8x. I hope I was correct here. 8x plus x squared. Cross multiply on both sides. You will find eventually that x If you use the just the typical, you cross multiply and then you use the formula, you find that x is equal to 1.5 meters. That means that x must be placed, that the 50 kilogram ball must be placed 1.5 meter, 1.55 meters from the 2 kilogram object. Okay, and we can actually test that. Okay, if we plug in 1.5 into this force, our original forces, if you plug in 1.5 and you calculate the force between this 50 kilogram ball and the 200 kilogram ball, you'll get a force. Now, if you plug it in between, you plug in the distance 4 minus x, and you calculate the force between the 500 kilogram and the 50 kilogram, you'll find that that force will be exactly the same, but in the opposite direction. Okay, so that is our first question, and then let's go to the question that we were reading earlier, but we did not do because I wanted you to see the actual picture of the situation. Okay, so let's go to the picture. There's the picture. Three uniform spheres. Okay, question 2. We have three uniform spheres of mass m1, m1 which is 2 kilograms, m2 which is 4 kilograms, and m3 which is 6 kilograms. Okay, and they are placed at the corners of a right angle triangle as shown in that figure. Calculate the resultant force on the object of mass m2. So the one at the corner, we need to calculate the force on that one, assuming the spheres are isolated from the rest of the universe. Okay, so the force between mass 1 and 2 is equal to, so F1 and 2 is going to be attractive, so it will be upwards. They even provided us with the directions. So it's going to be G multiplied by M1 times M2 over R. So it's 6,67 times 10 to the negative 11. And then the mass of M1 is 2 kilograms. And the mass of M2 is 4 kilograms. And the distance between them is 3 meters. And then you need to square the 3 meters. And of course, you can, if you want to, you can write it as in the j hat direction, upwards in the j hat direction, positive j hat. So if you work this out, you get 5.93 times 10 to the negative 11 newtons in the j hat direction, so positive j hat upwards. Now the force between number 2, between mass number 3 and mass number 2, G m1 m3 over r squared. That's 6,67 times 10 to the negative 11 multiplied by the mass m2 m3. That mass is 6 kilograms. The mass of m2 is 3 kilograms, or rather not 4 kilograms. Over the distance between them is 4 meters. And you square that. If you work it out, the force between them is 10. Oh, by the way, this is 5,93, not 593. 5,93 times 10 to the negative, this one is 10 times 10 to the negative 11 newtons. And this is in the negative I hat direction. So we now have a force going towards the left and a force going upwards. We need to find the resultant force. F net, I'm going to write it in just unit vector form. So F net, therefore, is just going to be negative 10 times 10 to the negative 11 in the I hat direction. That's negative I plus, and then of course in the j hat direction we 5,93 times 10 to the negative 11, and that is in the j hat direction, positive j hat direction. So there we have the net force on that, the resultant gravitational force on that. Of course you can put a triangle like this and then find the resultant, the net force, and then of course you work out the angle there, theta. So that is what we did on gravitational acceleration. Now I want to check on something before I continue. I'm just going to switch back now to our tutorial problems. There we have. We are done with that. Those two, I want to make sure. This is a fluid mechanics question. I assume you're all busy with fluid mechanics, so I'm going to do this fluid mechanics problem. It has to do with buoyant force and so on. So I'm going to go to the section on fluid mechanics on the textbook and then do those problems. Let me just recap some fluid mechanics you should know. Okay, I have it. Just want to make sure that those problems are from the textbook too. Okay, it is from fluid mechanics. And now a quick recap on fluid mechanics and what you should know. The pressure, okay, the pressure in a fluid at rest varies with depth, okay. So the pressure at a certain distance underneath the water, okay. So pressure varies with depth. Pressure varies with depth. According to this law, it says that the total pressure is equal to the initial atmospheric pressure plus the density of the fluid it's in times the gravitational acceleration times the height or the distance it is beneath the water. Okay, usually it's water in this case. And then the buoyant force, according to, by the way, Pascal's law states that when pressure is applied to an enclosed fluid, okay, like a closed pipe, the pressure is transmitted undiminished to every part in the fluid, okay, on the walls of that container. Okay, so according to then Archimedes' principle, the buoyant force Just want to check. Yeah, buoyant, buoyancy. So yeah, buoyant. Yeah, why? I'm almost wrote an A. Buoyant. The buoyant force is equal to the following. B. The buoyant force is equal to the density of the fluid multiplied by G, the gravitational acceleration, times by the volume of the fluid displaced. That's how you calculate the buoyant force. Okay? And then, of course, finally, the flow rate equation. I don't know if we do it on the side. Am I going to do some problems on the flow rate equation? I just want to check my other problems. There's a buoyant force, so no flow rate. Okay. So I'll use this pressure varying with depth and then the buoyant force. Okay, that's all you need to know for these problems, which is deceptively simple. A swimming pool has dimensions of 30 by 10 meters. A swimming pool has dimensions of 30 by 10 meters. The pressure on the bottom due to the water. Oh, let me just make my notes here. Correct. Check the problem. Okay, so a swimming pool has dimensions 30. The dimensions of the swimming pool. It's 30 meters by 10. 30 meters by 10 meters. That's the dimensions of this pool. And it has a flat bottom. When the pool is filled to a depth of 200 meters with fresh water, what is the force exerted by the water on I1, the bottom, 2 on each end, and 3 on each side? Okay, so how do we attack this problem? This is just a problem of pressure along the bottom. So if you calculate the pressure, you can calculate the force. So this is the pool in this case. This is the dimensions of the pool. You have that it is filled to 2 meters. It has a length of 10 meters or a width of 10 meters and a length of 30 meters. Okay, this is how I picture this pool. So there's the pool filled with water up to 2 meters. Right? We need to calculate first of all the pressure on the bottom. They need to calculate the force exerted by the water on the bottom. So let's calculate the pressure on the bottom. Okay, what's the pressure on the bottom? PB, pressure on the bottom. Okay, so PB, we need to first calculate what is the pressure. We've just from our summary now, we've established that pressure will be the atmospheric pressure, P naught, plus density times G times the height. Okay, there's just something I want to make sure of quickly. We do have a way of doing it. We just do it with an integral. But I want to make sure something. where we can avoid an integral, but it's not a big problem if we can't at the end of the world. So let's just see. I have it in terms of, by the way, we call this pressure the gauge pressure. Now the pressure at the bottom of the pool is uniform because the bottom is flat. That's why they told us that the bottom is flat. Okay, so the pressure at the bottom of the pool, uh, without the atmospheric pressure added, it's going to be just, let's just calculate. We are not going to add the, this is the gauge pressure, by the way. We are not going to add the atmospheric pressure. So let's just calculate the gauge pressure, and let's just denote the gauge pressure as PB, the pressure on the bottom. So it will be the density multiplied by G multiplied by H. Okay, this is how I got it. You can, of course, add the constant of the outside pressure, the atmospheric pressure. So the pressure at the bottom, or the density of water, and I had to go check, is 1,000 of fresh water kilograms per cubic meter, since we're working with dimensions in meter. Gravitational acceleration is 9,8, and then of course it is 2 meters below. So we now have the pressure due, the gauge pressure, it's the pressure just due to the water, not the atmospheric pressure as well. So it's 1,000 times 9,8 times 2. So that's 19,600 pascals. Okay, so this is just the pressure due to the water, not the pressure. And do they ask us there, what is the force exerted by the water? Only the water, not the atmosphere as well. So we only need to work out the gauge pressure. So there we have the pressure. But we do know that force, they want the force. We know that force. Remember, the pressure in this case is the same all over this bottom surface because number one, it is flat, and very importantly, it's flat. I don't know why I said number one, it's just flat. So the pressure will be the same all over. Now we know that force is equal to pressure times area. It's the gauge pressure times the area of the bottom. Okay, in this case, it's 19,600 pascals multiplied by the area of the bottom of that pool is 10 by 30, so 300 square meters. So 300 square meters. Okay, and that, ladies and gentlemen, gives you a force. If you multiply them together, you get a force of 5,8 times 10 to the 6. 5,88 times 10 to the 6 newtons of force. That's the amount of force on this pool, at the bottom of the pool, the amount of force due to the water on that pool. Now, you do the exact same thing for the sides. Okay, this is for number one, this is on the bottom, this is A. Let's work for it on the sides. I don't want to erase that, so let's do this. It's slower, but I don't want to erase. Okay, I will redraw my drawing. It's easier. So this is the pool still. And then of course we have that. This is the pool. And we have here 2 meters. We have 10 meters. And of course we have a length of 30 meters. So there's the pool. Now B, they want the pressure. The next question is the pressure on each end. Okay, so the pressure on each end. In this case, the pressure on each end, the ends of the pool, so we have vertical rectangles, right? Here it's 2 by 10 meters, so the area is 20 square meters. Right? Now the pressure on this wall varies with depth. Okay, so it varies with depth because the pressure at this point here, near to the surface, is going to be much less than the pressure close to the edge of the surface. Okay, so the pressure varies with the depth. So what we do here is we just calculate the average gauge pressure for this wall. Okay, so we take the average gauge pressure. So average pressure. In this case, you can do it using, of course, integrals, but we just take the average. But if you do integrals, you get a formula. We want the exact average. So the density times G times H. And that is just a half times what we've already calculated to be 19,600 pascals. So the average pressure on this wall is about 9,800 pascals. So that's the average pressure. Okay? And then therefore the average force then on this wall, the end walls, every, excuse me, I just went out. Please don't tell me I lost all my work. Okay, no, it's okay. So we have that the average pressure, we calculated it to be a half of the pressure that we worked out, which was 19,600 Pascal. Therefore, the average pressure is 9,800 Pascals. So that's the average pressure. And then, of course, the area for that endpoint, the area is equal to just 2 meters by 10 meters is just 20 square meters. So the force on the end wall, is equal to the pressure, the average pressure, multiplied by the area. So it's 9,800 pascals multiplied by 20 square meters. You get a force of 196,000 newtons. That's the force on the end wall, the average force in this case. And then we do the exact same for the sides. Okay, it's of course the exact same thing for the sides. You just use the average. See, if you do it for the sides, it's the exact same thing. You use P average because it's going to be the same for the ends and the sides, multiplied by the area of the sides, which in this case, the area is equal to, that is 2 by 30, so it's 60 square meters. So the average pressure is 9,800 Pascal times 60 square meters. You get a force of 5,588 kilonewtons. So 588,000 newtons. So 588 kilonewtons. Okay, that is the pressure. Now gauge pressure is the pressure without the added atmospheric pressure. Question number 3. Let's see. That's 588, 196, and 555. Those are the answers you should get. Now, a table tennis ball has a diameter of 3,8 centimeters and an average density of 0,0840 grams per cubic centimeters. What is the force required to hold it completely submerged underwater? Okay, so how much force do you need to hold this ball underwater? Okay, so in order for you to hold it underwater, the ball must not move, it must just stay still, not bob around. So the sum of the forces will be zero if you submerge it. That means the force, the buoyant force, uh, even if you subtract the force that you apply, the buoyant force minus the force you applied plus, there's one force pushing it upward, it's the buoyant force, and then there's two forces pushing it down, it's the force you apply plus the force of this ball's weight. The weight force not going to be much, but it must still be included. Okay. Therefore, you can say that the buoyant force is equal to the force applied plus the force of gravity. Right? That's simple math. So the buoyant force must be equal to the force applied and that of gravity. Now you already know what the buoyant force is. You can work out the buoyant force and you can work out the force of gravity. Okay, so let's first work out how to calculate everything. Okay, well, how do we calculate the buoyant force? We know that the buoyant force is just density multiplied by the volume of water displaced multiplied by g, the gravitational acceleration. The force applied is what we want, and plus the force of gravity. But we do not have the mass of the ball, or do we? They tell us the density of the ball and its diameter, so we have the volume of the ball. Okay, so if we have the volume of the ball, we have its mass. Just want to check. So the mass, we know that's the volume. We can work that one out, and the density of the ball. Force applied, and here. Okay, so PVG, that's the density multiplied by the volume of the water displaced times G times the force applied, which I just denote FA, plus the force due to gravity is just mass times gravitational acceleration. That's just G multiplied by the mass. In this case, we are not given the mass, but we do have the volume. Okay, and we have the density, and we know that density multiplied by volume of the ball should give you the mass of the ball. Okay, that is the density of the ball. That is the force applied, and here this is the density of the water, and here is the volume of the water displaced. So there we have a formula with all of our unknowns in there. We can now just make, we want the force applied. So by rearranging the equation, we get that the force applied is equal to V G, volume of the water displaced, times the density of the water, plus, which is, no, it's subtract. Take it over. You subtract minus the weight of the ball. Okay, and the weight of the ball is nothing but the gravitational acceleration times the volume times the density of the ball times the volume of the ball. Okay, you can simplify this by taking g out. It comes in both. G can take out, and of course the volume here is the volume of the water displaced will be the same as the volume of the ball. So you can take the volume out as well. So we'll have the density of the water minus the density of the ball. And that will give you the amount of force applied that you need to keep this tennis ball submerged. Okay, now looking at this math, we have that the volume, or rather G, in this case 9,8. The volume of this ball, it's a spherical ball, so it's 4,3 times the radius. What's the 4,3 pi and the radius squared of cubed? What's the radius? It's half of the diameter. Half of 3,8 is 1,90, but we are writing it in meters. So 10 to the negative 2. You cube that, so there we have the volume, and then multiply it by the difference in their densities. Okay, water has a density of 1,000 kilograms per meter per cubic meter. By the way, they did not say clear, it's clean water. Obviously, it changes if the water is different, or say chlorinated water, like in a pool. And then the ball has a density of 84, 4,0 kilogram per meter. That's simple unit conversion. And if you work all of that out, the force applied, if you multiply that all out on your calculator, you get 0.258 newtons. So 0.258 newtons of force is required to hold this ball down, and that is what they give there as well. 0.25 newtons of force. So question 4 for this session: a cube of wood having an edge dimension of 20 centimeters. So we have a cube. Okay, so all its edges has a length of 20 centimeters, and it has a density of 650 kilogram, and it floats on water. Okay, what is the distance from the horizontal top surface of the cube to the water level? Okay, how do you work that out? Why is that a problem? Remember, the wood is not completely just floating on top of the water; it is slightly submerged. Okay, now the cube has a side of length L. Okay, 20 centimeters. So it's called L. Now, when floating, the top of the surface is a certain distance away from the water surface. Okay, the buoyant force supports the weight of the block. They want to know what's the distance from the horizontal top to the water level. Okay, we know that the buoyant force B is equal to the density of water times the volume of the object. That's the amount of water displaced times G, the gravitational acceleration. Now, what is the volume of the object? Okay, so we have, first of all, we have the density of water times the volume of the object. What is the volume of this object? Okay, now note, let's call it just L in this case. It's going to be L cubed. Remember, volume is L cubed. Okay, but in this case, the height changes. It's not going to be the same. It's going to be slightly inside the water. So it's going to be L. The volume should be L times L times L in ideal situations, but it is slightly submerged. So it's L times L times L minus H minus the height it is submerged in the water. And then of course times G. Now, this is the amount of buoyant force that is required to hold this thing up. But we do know that the weight of this block will be equal to the density of the wood, as we saw earlier, the density of the wood multiplied by its volume, which is L cubed, and multiplied by, so this will be its mass times gravitational acceleration. So this we have one formula equal to this one. Okay. Now if we make h the subject of the formula, if we make h the subject of the formula, you can do this by yourself, but if you do make h the subject of the formula, you get that it's L minus L times the density of the wood block, the density of wood, over the density of water. So this is the formula you have. You equate this one to that one, and then you make h the subject of the formula. Simple math. And you can then further simplify this by taking L outside. You're left with 1 minus density of wood over density of water. Okay, so it is then the length is 20 centimeters. I'm just going to use centimeters times 1 minus, what are the two densities? The density of wood and the density of water. That of wood is 650 kilogram per cubic meter, and that of water, as we've established now, is 1,000 kilogram per cubic meter. Therefore, the answer then is 7 centimeters. Okay, so 7 centimeters of this block is from the top to the surface of the water. So 13 centimeters is underneath the water. Now, let's see what mass of lead should be placed on the cube so that the top of the cube will be just level with the water surface. Okay, so we want to further, it's like the same with the applied force in the previous question, but in this case, the applied force will just be the weight of the lead. Okay, so in order for it to be completely submerged, the buoyant force must be equal to the force of gravity of the block itself plus this mass of lead that we were introducing multiply plus the weight of this lead. Okay, and m is the mass of the lead. M is equal to mass of lead, Pb, lead. M is the mass of the lead. Okay, so the buoyant force is just the density of the water times the weight of the water displayed. That is just the volume of the water displayed. That's just the volume of the block, L3, and then times G. And that should be equal to the force of gravity of the block, which is P, the density of wood, that's the mass, times its volume L cubed, times G, that is the mass, the gravity, the gravitational force on the block, it's just the mass here. Density times volume is mass, and that multiplied by G is the gravitational acceleration, plus M, which is what we want, times G. Now we can still see straight off, we can cancel all g's. And if we make this the subject of the formula m, we have that m is equal to L, density of water, L cubed minus density of wood, L cubed. So we can actually take out L cubed, which is the volume of the block, and then it's just the density of water minus the density of wood. And that is just 20 centimeter block. Here they have it as 20 meters. It's 20 centimeters. Okay. Oh, they divided that by 1,000. So here you have 20 times 10 to the negative 3, and then the density of water is 1,000 minus that of the 650, and that should give you 20 times 250, which is 500. Oh no, it's 0.65. Rather just leave it like 2,80 kilograms. That is the answer. You should get 2,80 kilograms. Okay. And we won't be doing the simple harmonic question. That's why I added the other question. So I hope that was good enough. And I hope that you understand what we did. I thank you and I hope to see you again next week. Thank you.